Okay, so welcome everyone. Good day. It's my great pleasure introducing our today's speaker, Professor Daniela Calvetti. Daniela is a professor at the Department of Mathematics, Applied Mathematics and Statistics at the Case Western University in the US. She completed her PhD in 1989 at the University of North Carolina, Chapel Hill. Then she became assistant professor at the University of Colorado Pueblo and at the Stevens Institute of Technology before moving to Case Western University in 1997. Her research activity covers several areas of numerical analysis and large-scale scientific computing, with focus in particular on computational and statistical inverse problems and predictive mathematical modeling. Her research activity was acknowledged with several recognitions, among which I will only mention the James Wood Williamson Chair that she holds since 2013, and the Mother Spotlight Prize she received in the same year. Daniela is member of several advisory and prize committees, such as the George Polya SIAM Prize and the SIAM Outstanding Paper Committee, as well as member of the editorial board of internationally known journals, which I'm sure this community knows very well, such as, for instance, Inverse Problems and JMIV. She co-authored two well-known books on computational mathematics and Bayesian scientific computing. And her talk today will be on Bayesian reimaging of sparsity in inverse problems, which I really look forward to. So before leaving the stage to Daniela, just a quick reminder to the audience. As usual, if you have questions, just write them using the Q&A window or in the chat. And I keep an eye on that and read them to Daniela at the end, where we can also unmute people so that they can interact with Daniela directly. And Daniela, please, the stage is yours.
Okay, well, thank you very much for the introduction. That kind of like, made me feel self-conscious. And so thanks for the invitation to talk in this seminar. So what I want to talk about is something that I've been thinking about for over 15 years, and is interplay between Bayesian inference, scientific computing, and applications. So the talk that I'm going to give today is based mostly on work that I've done with Monica Pragliola, Erkki Somersalo, and Alex Strang. Monica and Alex, at the time when this was going on, they were PhD students. They're now doctors. Monica is at the University of Bologna, and Alex is at the University of Chicago. And I had to, acknowledge, their very important contributions to this. So. Okay, let's set up the problem here. And so what I will consider is a sparse linear inverse problem of the type that I've been sort of solving for, or trying to solve for 3 decades here. So let's say that we have a linear observation model, and the data are few, as are in, let's say, some of the inverse problems that arise in like medical imaging, non-destructive testing here. And so we have a few indirect and noisy observations. And I'm assuming here that, I'm assuming that the noise is additive and Gaussian. This is a simplifying assumption. There is quite a lot of notation to go through. It can be extended to Gaussian noise with positive definite covariance matrix, and through whitening we can reduce it to this case here. Non-additive noise has to be dealt with separately, so it's pre-processed to be of this type. So if we have this type of observation model and this type of additive noise, then we can write the likelihood, which is essentially a way of expressing in probabilistic terms how likely it is that we're going to get the data that we have for a given value of x. So it is a probability of B is observation given that we know what x is, and we write it in this format here. This is a fairly standard and, let's say, uncontroversial. It's one of the few uncontroversial things about this Bayesian framework here. Now, now we start with let's say, subjective part. So a priori, okay, a priori we assume that the x, the value of x, the vector x that we're looking for, is sparse. Now, this is a belief. And since this is a belief, we will treat it, as such and frame it appropriately. Another way of saying that X is sparse is to say that the cardinality or the zero norm is much, much smaller than the number of components of X. Sparsity is, I usually say that sparsity is a frame of mind. Actually, sparsity isn't the representation. So we may have signals, and many of them that we're considering are not at all sparse themselves, but they admit a sparse representation, meaning that X may be fully, may have the support over the entire set of indices here, but can be expressed as a matrix L times a vector Z. And if the vector Z is sparse, well, then we will generalize the idea of sparsity to the representation. And I will not follow, stop a second. I'm not following the chat here. I will continue. If there is, if I should stop, Luca, please feel free to interrupt me. So sparsity is a belief. Sparsity is a belief. That's my idea of taking sparsity and give it a Bayesian spin here. So since sparsity is a presumed property of the vector, then we will go ahead and try to use what we know a priori as some sort of additive information when we're trying to solve the problem, because after all, if we're doing an accounting, like the back of the envelope count, the number of unknowns that we have to determine is much, much larger than the number of equations that we have. So we need to augment the data with some qualitative. Now, here I have a list of different ways of representing. So we could have sparsity in the standard coordinate system, sparsity in wavelet basis, Fourier basis, first order difference in matrices. I will show some examples of this, and also sparsity maybe in terms of representing a signal in terms of a dictionary that has been given to us. And that's an application to data science, which, by the way, is one of my latest interests since I've been teaching it, and there is a book coming out soon. So the literature on sparsity and how to solve sparse inverse problems is fairly rich, and there is a lot of work that can be found about the power of using L1 penalty. And I have to say that this was actually the reason why I started thinking more deeply about sparsity and in the Bayesian framework, because Alex went to a Golub summer school in Berlin where they were talking about L1 magic, and as we were talking about what we had learned, well, then we started revisiting it. It was very fruitful summer school for him and for all of us. So what we know is that if we penalize, so the way in which we usually promote certain properties of a solution is we put a penalty for deviating from what we expect to be the case here. So penalizing with LP penalty terms, if with P strictly less than 1, it's even more effective at promoting sparsity than penalizing with L1. There is a little bit of a problem, and the problem is that what we end up doing when we get to the computation is we have to find minimizers of functionals that are not non-convex, and the problem is that we may stop at a local minima, which is not the desired one. So that's not ideal. So it's ideal in the, let's say, the properties of the sparsity promotion, but not in the computation. So we try to overcome this. And this is just to show you how different, let's say, LP penalties, how, why they more or less strongly promote sparsity. So this is the breakpoint here. Here is not sparse at all when we're down to P greater than 1. And when P is less than 1, the sparsity becomes rather extreme. And in the end, we're just going to have a cross in 2 dimensions. So in the Bayesian framework, everything that is unknown deserves to be modeled as a random variable. That's pretty much the mantra of the Bayesian framework. All parameters in the likelihood, unknowns that we want to compute, parameters that describe the unknowns that we want to compute. If we don't know them, they're going to be modeled as a random variable. So now we need to figure out how we reformulate sparsity as belief in the Bayesian framework. What does it mean? So if we were to talk over the phone, without formulas here, we would say that something is sparse if most of the entries are equal to 0. So, however, not every entry is going to be equal to 0, because that's not going to be a very interesting solution. It's not probably going to satisfy the data. But we have a few non-zero entries. But if we are real indeed sparse, those non-zero entries should be rare. And in the language of statistics, they've been considered somewhat outliers. There is another issue associated with sparsity, which is the one that makes the problem really difficult, is that we usually do not know a priori what is the location of the non-zero entries. Otherwise, we would just deflate the problem, just solve for the non-zeros, and the problem would be much simpler to solve. So we don't know the locations of the non-zeros entries, but we think that this set is going to be a set of small cardinality. So since sparsity is a belief, beliefs in Bayesian framework are encoded in the form of priors. So now we're going to go and formulate sparsity as a prior here. So, and my approach to sparsity, as is my approach to everything in life, is let's take the simplest approach and see if that works. And if not, we're going to make it more complicated. So same thing here. Gaussian distributions are really nice and easy to work with computationally. So let's start with thinking what we can do, staying Gaussian here. And well, it turns out that Gaussian alone is not going to be very sparsity promoting. However, what we can do here is we can model a sparse solution as a conditionally Gaussian random variable. And we want the components to be able to vary independently. So we're assuming that the pixels are uncorrelated, so they are independent of each other. So one can be 0 and the next one can be huge. And we're also expecting, so we want to also convey the idea that we're expecting that most entries will be 0. And in fact, computationally, we know that 0 is very difficult to achieve. Already 0 in MATLAB in IEEE arithmetic is 10 to the minus 16, which is not at all 0 here. So we're going to say that we will be happy to say that these entries are random variables with 0 mean, and if we want them to stay close to their mean, then we would like their variances to be small also. However, some of them, now there are the exception handling, there is exception handling portion here. We also have a few that could be actually of very large magnitude. So for those, this small variance is not going to be appropriate. So we would like those to have large variance. And the other thing is that we don't know where they are, so the support is unknown. So we have some, a random variable framework with, quite a few unknowns. Once we have expressed, we have condensed all of these, let's say, qualitative ideas about sparsity in the form of a prior, then what we can do is we can combine the wisdom of the prior with the information that comes from the likelihood and invoke a Bayes formula and correct the prior with the likelihood to get the posterior, which is the probability density of the unknown. And in the Bayesian framework, that would be actually the solution that we're looking for. We will deal how we represent the unknown, the posterior later. So let's just go ahead and a little bit some formulas here. So let's write down the conditionally Gaussian prior, conditionally because it's conditioned on having the is conditioned on having the variances that we don't know. But let's say if we knew what the variances would be, and I'm collecting all of them in this diagonal matrix D here, then the probability density of the entries of the unknown given theta would be, the Gaussian of this type here. So the fact is that and I'm trying to use color coding here to make it easier to follow what's going on, the game that's going on here. So this is all conditional on knowing theta, but we really do not know theta. So now we have to come up with a way of describing these unknown variances. So these prior variances here, and they have to be, they are unknown, so we're going to describe them probabilistically. They have to be greater than 0 because they're playing the role of variances here, and they're going to also be mutually independent. We're modeling them as mutually independent because, again, we want to allow the signal to change abruptly from one entry to the next, so without correlating values, and therefore variances in this case. So and there are many different ways in which we can choose the description of the prior variances. For computational conveniences, we actually decided that we're going to stick to the class of generalized gamma distributions, and which are described in this fashion here. And I'm not going to go over all of the details. I will address some of the numbers that arise in a second here. I want to point out that the nice thing, or one thing that makes this particularly attractive, is that there is an exponential part, which, in light of the fact that later we will combine the prior and therefore there's let's say portion of the prior, because that's an hyperprior, with the likelihood, then we have an exponential here, an exponential here, we have an exponential in the likelihood, they're all products. So eventually, if we decide that we're going to do something like fairly routine, like representing the posterior with the value of the unknown that maximizes it, well, then we know how to deal with, it's going to be more, let's say, computationally friendly. So now we have a way of describing the primary unknown, which is X, as a conditionally Gaussian, given some other unknowns, secondary unknown, which are the variances, which are the thetas. So the unknowns that we have are going to be the union of the X's and the theta. So what by formulating the prior in this fashion here, we have actually doubled the number of unknowns to be estimated. That seems to be not such a great bargain, but we'll see. And so these are just to show you why gammas here. Gammas because, we are, we can tune it so that we get the mean to be as small as we want to. And most of the realization will be close to the mean, but this gamma family allows for outliers, which is what we want in order to allow for some of the variances to become very large. So these are fat tail distributions, not the only ones. Now, let's put together the two pieces of the prior. So we join the conditionally Gaussian density of the prior. So we have the hyperprior. We will call this hyperprior because it's it's at the secondary level here. And the real prior that we're dealing with is going to be describing the pair X theta. So it's a probability density, the joint probability density of X and theta. And if we write the joint through the conditional, then we have this formula here. And then we're using also the independence assumption here to simplifying it. Then what we have is that we're gonna invoke a base formula. And when we look at Bayes' formula, we realized that what we would like to compute is actually the probability density of x theta, now the full set of our unknowns, given the data, so conditioned on the data that we have, meaning that, of course, if we're changing the data, and the data could be anomalous or could be very, very routine, but it will depend. It's all conditioned on what we're observing here. This is simply the product of the conditional density of x, the hyperprior, which describes the unknown variances here, and then we have the product with the likelihood. So now we're substituting, and this is where the cartoon should be then a miracle occurs, but it's only substitution here. And what we have is that after substituting the various expressions and bringing them inside the exponential, bringing inside the exponential everything that is not a constant that can be ignored, and that's this proportionality here. Also introducing the auxiliary secondary parameter eta, which is r beta minus 3/2, and that comes from the parameters of the gamma family here. We get an expression of this type. And this is color-coded for a reason. And the reason why it's color-coded is because, well, the blue part, which is pretty much the contribution from the likelihood, that involves the primary unknown x. The red part here, and you can think of the red part as being some sort of decoupling between the magenta and the blue. The red part depends on x, but it also depends on theta. And then we have all of this portion here, and this portion is only a function of theta. So we have some sort of separation inside this expression for the posterior. So to max, we could do many things when we have a posterior, and if we know how to do them, it's not super straightforward to sample, when you have this hierarchical models where you have two levels of unknowns, one that depends on the other one. One simple way of producing a solution which is kind of like the probabilistic counterpart of the deterministic solution of an underdetermined linear system here is to compute, to summarize the entire distribution with one value, which is the value of the unknowns, x and theta, that maximizes the posterior. And maximizing the posterior is equivalent to minimizes the negative logarithm of the posterior. And this is the negative logarithm of the posterior. It's also known as Gibbs energy in the field here. And we have two parts. So I'm gonna actually slice it a couple of different ways. So we have this part A, and this is grouped together because it involves the unknown x here. And then this part, and I call it P of x theta, which involves x, but and also theta, which is, so if you try to do matching with traditional regularization methods, this would be the what takes the place of the regularizing functional. So the regularization functional in this setting is written, well, and it's an algebraic expression here. It's not that there is no probability anymore, but it's written in terms of the probabilistic assumptions that we make about the unknown, the primary unknown, which is x, and also its variance, which is theta here. And the way in which we proceed when we want to minimize this Gibbs energy is we alternate here. So we start with some initial values. So we're setting the initial variances to this var theta unknowns here, and you say, okay, now we start sweeping under the rug because there are going to be parameters to set that is correct. I mean, there are parameters that we will need to set, and I will address this in a second. I'll actually give a pointer to that. We start with assuming that the signal is totally zero, totally vanishing, so it's x0 is equal to 0. And we start alternating with this algorithm, which was, was named, I think was Samsa person who named it Iterated Alternating Sequential algorithm, because we keep, it's a very natural inner-outer iteration here. So the outer iteration are composed of two steps here. The first one is we update X, assuming keeping theta fixed. So we minimize, I called it E, this is F, the Gibbs energy with theta fixed with respect to X. That's going to give us a value, a new value for X. Then we update, so we're using the most recent information about the unknown, and we update the variances by minimizing the same functional here, but this time is going to be the magenta part, which is going to be involved here, because the minimization is with respect to theta. And we just keep doing until, well, until we satisfy stopping rule. And the stopping rule is very much inspired by the stopping rules that are used in typical minimization optimization algorithm. Go back to the classics, Danish Nabel chapter, I think it's chapter 7. So let's look a little bit at the details here. And now that's when first love is never forgotten. Numerical linear algebra is always everywhere in my research. So let's say that if we're fixing theta here, the new value of X is the value that minimizes this expression here. And minimizing this expression here is the same as, and the thetas here should not be squared. Sorry about this, it's a typo, because these are already variances, not standard deviation. So we can work backwards, and we can say that finding the minimizer of this expression is the same as solving this linear system in the least square sense. Which way we solve it? Well, this is going to be pretty much up to us. If we have the computational resources and the time, we can use a direct method. If we do not, also we need to have the matrix A available. The matrix D is a very cheap matrix. If we're also into doing things a little bit faster, then I'll show what we can do. We can take a shortcut, and instead of solving exactly this least squares problem, we can solve it approximately, and this is it's very much a setup for preconditioned conjugate gradient least squares. So let's say the two steps are fairly straightforward. The first one is just the least squares, and the second step is the update of theta. Then it's done component-wise. So we can just go ahead and write down the first order optimality condition, and we update theta. We can do it component-wise and just solve it. And it turns out that, this would seem to be more complicated, but for some members of the family, in particular for the gamma and the inverse gamma, we have an analytical expression, so it's just formula evaluation. And for the other ones, there is a nice way of doing it numerically, and a little technical, but very straightforward. So just a couple of, just one slide here on working on reducing the model here. It's amazing in some ways how Clear subspace methods, they sniff and they seem to understand, even before we do, what is the true dimensionality of the problem here. So let's say that we have a matrix A, and that is large, and so we don't want to solve this directly. So instead of solving, so we could solve this with conjugate gradient for least squares applied to the full problem here, but in that case we are putting in some ways the regularization already in the lower part. This is like a let's say least squares weighted here. We instead, what we want to do is we're going to make a change of variable, and by introducing this auxiliary variable W, which is related to X via the matrix of the thetas, and this matrix is a matrix which is updated at every outer iteration, we can concentrate, essentially we're concentrating on the top part of this system here. So instead of solving the big problem and going to full convergence, and that will require quite a lot of conjugate gradient least square steps, we can just solve approximately this reduced this reduced problem here, a d theta to the 1/2 w equals b. And we solve this using the conjugate gradient for least squares equipped with a stopping rule. So we're going to put a stopping rule, and the stopping rule is a mix of a discrepancy principle, meaning that we're not going to solve this more accurately than there is noise in the right-hand side B here, but also we also keep in mind in our stopping rule that this small least squares problem is really a proxy for a larger least square problem, and at every step we can check how the proposed solution proposed for the larger one that we can get simply by rescaling of the components, how we are doing in terms of decreasing the discrepancy, the residual for the larger one. So when we stop solving, making progress towards solving the larger one, or when we have reached this solvability in light of the fact that we're working with noisy data, we stop. Now, every conjugate gradient least squares iteration only requires one matrix vector product with matrix A and one with a transpose. Scaling the vector here is cheap because this is a diagonal matrix. And it turns out that if the thetas, as the theta j's become small, which means that as the variances converge towards, their minimum possible value, which is determined by the choice of gamma parameters in the gamma that we have, well, essentially the corresponding columns of the matrix A, d theta to the 1/2, they are, one can think that they get deflated. So they weigh much, much less. And it's equivalent to effectively reducing the dimensionality of the problem. And in the end, effectively, when we're solving this small least squares problem, we're solving a problem which is, contains information about the dimensionality of the original one. That has not been, so we have made some progress towards how this is emerging in the CGLS. Still, there are a number of open questions there. So this is part of the theta update. And all I want to say here is that in general, the way in which we update theta is that we have a function. So the new theta are going to be functions of the most recent approximation of the solution x. And we have this function g, which is an invertible function. So we can go back and forth between the thetas and the xj's. And that's a really nice correspondence. In the papers that are mentioned, there are all of the technical details. Some of them are sort of heavier. Now, for some of, not all members of the generalized gamma family are equally, let's say, rich in good properties. But, there is some good for all of them. It's the gamma hyperprior, which is the one that corresponds to R equal to 1, is, has the property that the functional f, the one that we're minimizing here, turns out to be strictly convex and has a unique minimizer, which is really nice because it means that our algorithm, our iterative algorithm, actually will converge towards a unique solution here. And in fact, we have some theoretical results already established in 2015, together with Francesca Pitolli, Barbara Antaccio, and Annalisa Pascarella, where we're actually showing that essentially as we're taking the parameter eta, which was related to the beta in the gamma distribution. As this goes to 0, the penalty, our penalty term here, reduces to a classical weighted L1 penalty term. So we can think that if we're taking a gamma hyperprior and if we're choosing a parameter eta very, very small, we are doing in a Bayesian way the equivalent or something which is almost like solving the problem using an L1 penalty term, except that we have the Bayesian interpretation and Bayesian framework here. And so in general, these nice properties of convexity are not shared by all of the members of the generalized gamma family. So the next best, if we don't have, if it's not everywhere convex, is, well, what can we say about our problem here? So before I move on, and I thought I discuss a little bit convexity and conditional convexity. So we have, on some portion of the domains, we can guarantee that the functional is convex, and therefore we have the unique minimizer. I want to mention that in the setting at the beginning of our iteration, we were setting the variances to be equal to the theta, bar theta j's, which are parameters of the generalized gamma. Now, these are known as scale parameters, and it turns out actually that they play the role of sensitivity weights in inverse problems. So now we have a way of justifying in a Bayesian framework why we can use sensitivity weighting. And also we have a way of setting these, the values of these parameters automatically from, let's say, a measure of the signal to noise ratio in the problem, and from this, the norm of the columns of the matrix A. So now we have some results on convexity and sparsity promotion. So if we have, so if we're going into the family of gamma hyperpriors, so right now the Gaussian, conditionally Gaussian is very calm and practically inert. It's there waiting for the variances to come in and determine which entries will stay close to zero and which one are likely to, let's say, jump and take on values different from zero. So it's all played, the game, it's all played on the hyperprior. So let's say that if we're looking in the gamma family for the members that correspond to R greater than or equal to 1, so starting from the gamma and on, and if we're choosing the parameter eta, which is R times beta minus 3/2 to be positive, then we have the guarantee of having a function, the functional to be minimized to be everywhere convex. And that's nice, from the point of view, given that we're going to minimize it, that's a very desirable property. But not everything is lost. That's a silver lining, let's say, in not having all of the properties. So what happens if we're taking R smaller than 1, between 0 and 1, and R between 0 and 1 would correspond, there is a correspondence with LP penalties with P less than 1. So again, for choosing eta in the same fashion, or even, we can even go to generalized gamma with R negative. Then we have some conditions. So if the thetas are less than certain parameters, the theta j's are less than theta bar, theta j bar here, which is related to this expression, which depends, again, it depends on all of the parameters that determine the member of the generalized gamma, then the functional is also convex. So we have conditional convexity. So we have a convexity region, and this convexity result here is expressed in terms of the variances, but since there is this function g that is invertible, the one that determines the update of theta in terms of the x's, then we can sort of pull it back and express this convexity region for the values of x. So we have some regions where actually the functional is convex. It's not the entire domain. And this is this looks like some sort of ceramic, some tiling of some artwork, and this is that was Alex's doing here. And so what you have here is you can see that the convexity region in R2 for 2 dimensions here, and that's the one which is enclosed in the red rectangle here, red square. And R equals 1 is here. So the way to be read is that here we have no box because the box is besides the point. So it's convex everywhere. And here we have that the region of convexity in this region here, where the sparsity promotion is fairly strong, will depend on the way we choose eta. And for some is very, very limited, and then it becomes larger here. So one can actually look at this and can do a table lookup, and one knows more or less what one is giving up in terms of promoting more sparsity and foregoing, a wider region of convexity. And this is the same for negative values of R. Not intuitive, but so this follows from, say, calculations. And now, yes, so this one makes some parallels between classical penalty terms and this distribution, generalized gammas here. So what we have is that we get the equivalent of LP penalties by choosing certain parameters in the gamma, and the P. So, and here it is what correspond to making eta equal to 0, which is the same as taking R beta to be 3/2. And that would correspond to an LP penalty where P is 2R divided by R plus 1. So there is a parallel between the classical regularization with LP penalties and there's a Bayesian regularization with hypermodels. And okay, these are level curves of the penalty. You see more penalty promoting. R is 0.25, R equals 1, classic type L1 type, and R equals 4, not much penalty, not much sparsity promotion here. And now the idea is like, can we have the best of both worlds? Usually is no. The answer is no, but it doesn't hurt to try. As they say, you don't win the lottery if you don't at least buy the ticket. So we started thinking, why not building a hybrid scheme where we combine the guarantees that come from the convexity with, at least in the beginning, where we don't know where we're going, so the convexity is going to guide us in the right direction, with a stronger sparsity promotion once we start, finding our way. And to do that, we considered actually 2 sets of parameters, so to speak. We're keeping into the game 2 different types of hyperpriors. One which corresponds to, let's say, which will give us function which would guarantee global convexity. And these are the corresponding parameters. And the superscript 1 is the, let's say, phase 1. Where we're choosing R to be at least 1 or larger to guarantee convexity. And the second one, well, in the second phase is when we start becoming greedy, saying, okay, we're making progress to get towards getting a sparse solution now. Let's go faster there. So let's see what happens if we, let's consider using a hypermodel where the convexity is only local. So these are, so we write up the 2 corresponding hypermodels, and the only change is going to be in the penalty part, because the likelihood, the data, let's say, the test with the data remains the same. The data remains the same. So we have these models M1 and M2. And again, in the first case, we don't have anything to worry. The convexity is guaranteed everywhere in the domain. And for the second model, we have these, let's say, threshold parameters, the threshold values of the variances. They are indicated with a bar on top, theta bar j. And we're going to have that as long as the modulus, the absolute value of the xj is less than this computed value here that we're going to call x bar j, then we're also staying we're also in a region of convexity, even when using this sparser, or say greedier hypermodel. So this will appear, this is all described in the details in a paper that is about to appear in CISC. So the strategy, we have two strategies. Now we have to decide, like every hybrid scheme, you know, we have the pieces, now we need to make them work together. So we have a local strategy and a global strategy. The local strategy in some way is the more secure, the more conservative one. And we proceed surgically. It's almost, we're tracking. This is, you know, these days of COVID, you know, this testing and tracking is, so we're actually testing every time if the theta j's are, which theta j's, and therefore which pixels, you know, are in the region where if we were using the second hyperprior, we would not disturb the, we would not lose convexity. So we proceed only updating the hyperprior for those entries that are within, let's say, the convexity region for the second, for the greedier hyperprior here. So at the time of the update, we compute the update with, you know, for theta j's according to the current model. And if we are, if we pass the test, then we update with the new one. Otherwise, we go with the old, let's say, safer option here. So that means that as we move along, we are actually keeping two indices, two sets of indices. So we're partitioning the indices of the entries of the solution vector into those which are in the convexity region for the second hypermodel I and the complement of it. And when we're writing the energy functional, the one to be minimized, it's going to be a mix instead of, so we're going to split the summation and we're going to use one expression for those which are not, which have not passed the, say, the convexity test. And we're going to use the second greedier for those for which the theta j's is below the threshold theta bar. And then we need to sort of, this is easier said than done, like many things. So we need to actually take care of the details. And in assembling an algorithm here, what we do is we want to guarantee some continuity of the hyperprior. So, again, we're going back and we're reasoning about what these quantities mean. They're all interpreted. And the story is that if we had the xj be equal to 0. So if the signal were indeed, you know, 0 vanishing here, then in some ways, what we would say, we want to say about its variance, that would be the ideal case, like we are at the expected value. But then our information about its variance should be the same regardless of the type of hypermodel that we're using to describe it. So the first matching here, we do it by essentially making sure, by choosing the parameters of the second model in such a way that the update when x is equal to 0 with both hypermodels is the same. And that gives us a formula for choosing the parameters theta var theta j in the second. In the first one, we're choosing it according, for example, to sensitivity. And then what we want is, we want to have some stable convexity in some way, meaning that we want to say that, so we can we have some results as to when things are guaranteed not to, you know, to keep getting smaller. However, in general, computationally, what we want to say is that once we enter the club of the indices where the second hyperprior is conditionally is convex, we don't exit. So for those that have, like those that have entered there, when we update the value of x, we will make sure that they stay in by projecting into the interval minus xj bar. So under this condition, what we get is that we work with a functional that is and remains globally convex. Does it work well? Yes, it works quite well, and I'm going to show you some results very soon, very soon. But it's slower, like most methods that have a guarantee of, let's say, convexity of good properties. We pay a price for it. So if we want to do a faster, if we want to move a little bit faster, then we tested this, and this is more heuristics, this global hybrid strategy here, and is the following. We perform a fixed number of iterations, of outer iteration, and I call it T bar. So T is T almost like time, but really it's an iteration index. And with using only the hypermodel that is yielding a convex functional, so the first one. When we are at T bar, regardless of whether the whether the convexity condition is satisfied or not, everybody changes. So we're changing all of the hyperpriors for all of the variances here, and we switch to the second model, M2. So this is a global, we call it global because we make a global switch. So what's the rationale for doing this? The rationale is that since the first one, the first hypermodel is actually working with a convex functional, well, the iterations will lead us towards the minimizer there. And if we made a few iterations, well, the hope is that we've gotten close enough to minimize that is meaningful for the problem, and is say intermediate result is going to be a good enough initial guess for finding the global minimizer of the second functional. And again, for the second functional, there are problems because this is non-convex, so we could have several local minima. But we're assuming that we're getting into a region where any of the local minima that we might end up converging to, because that's what minimizers do, will be acceptable, will give us a good approximation of the solution that we're looking for. After all, we're working with noise in the data. And,
I'm sorry, Daniela, to interrupt. You have 3 more minutes. Okay. We're running a little bit late, sorry.
Sorry, yes. So I'm going to show very quickly here the numerical results. So this is the parameters. I'm going to show the results for the gamma hyperprior and inverse gamma. And for the global hybrid, so I will take this signal here. This is our generative model. It's sparse, let's say in the increments. Of course, it's not a sparse signal, but it can have a sparse. It has a sparse representation. This is the blurred and noisy data. So under, it's an underdetermined linear system here. And we're solving, so we're gonna go ahead and we're solving it using the gamma hyper model, the inverse gamma hypermodel. So not so greedy and pretty much global convergence, but not so sharp either. Inverse gamma, much greedier, no guarantee, and is doing a beautiful job in this region here. It's missing one of the increases here. Then we're going to have the local hybrids where we're combining this one and this one with the local strategy, so surgical switch. And this is the result that we get. And then we get the global hybrid. We run 10 steps with R equals 1 with the gamma. Then we switch to the inverse gamma. And at that point, the gamma has already found that there is something happening in this region here. So the inverse gamma is bypassing the lure of sort of skipping this and is actually finding all of the jumps. And what we're seeing here is these are the thetas. So these are the variances. And you can see that the variances are very, very small. These are the order of 10 to the minus 6 here. In all of the background where there is no activity, but in connection with the jumps, we have outliers. As expected, this is the number of conjugate gradient least squares iteration in the different iteration. In this case, we're doing 25 iterations, and you see that in the end, there are exactly 5. And in the beginning, there weren't all those many. There were like 6, 5, 6. 5 again for the inverse gamma, 5 for the hybrid, and 5 here. So, you know, the conjugate gradient for least squares does a better job, actually. All of these were solved, you know, approximately looking at a small problem. And this is how the yellow ones are those that satisfy the condition for convexity. Let me see, no, the green ones are those, yeah, that satisfy the condition for convexity. The yellow one don't. So you see that in the global, there is a bigger mess in the beginning. This is after we've switched. And then at some point, the greediness is guiding to really reduce the number of status. And then we have a couple of 2D examples. So this is an example with a QR code. So it's 136 by 136. We're observing this one, corrupted Gaussian blur, additive Gaussian noise. And this is expressed in terms of the vertical and horizontal. So there is some technicality here. This can work for 2D, but, you know, so there is some linear algebra details found in the book, in the paper. And here, these are the reconstructions. And you can see, I think it's faintly visible after 30 iteration with the gamma, the inverse gamma, and the global hybrid is almost perfect here. So the difference is one would have to zoom in into the details. And this is how the, let's say, how the thetas come out here. And we can also look at how there is a switching to, you know, satisfying, let's see if it works. Yeah, well, it doesn't, you know, there is supposed to be a movie, but I guess it refuses to make it work, and probably safety over Zoom. And then we did the same with a signal which is truly sparse in its own, on its own, which is a starry night. And this is the observed. And again, we're doing the same thing, gamma, inverse gamma, local hybrid, and global hybrid. And you can see the number of iterations. When you're going greedy, we're greedy everywhere. We have fewer iteration, and we have, you know, let's say, a lot more sparsity. And I want to just point out that in the gamma, safe and sound, here, it's starting to see the second, starting to see the second star that we see in this cut here. The inverse gamma cleans up the sky beautifully, but it misses one star. The local hybrid sees the one star, the intensity is not as high. The global hybrid does a great job. And again, then we can use this also to apply to this, to dictionary learning. So we have a dictionary, let's say the usual MNIST handwritten digits. I guess the post office these days is primarily featured in the United States with all the ballots that they have, you know, to deliver. So, so we want to classify, so we have annotated data. We want to express it in terms of, you know, what a new data, a new sample we want to classify. And so we want to decide which digit it is. And we're using the hybrid scheme, and just without the details, you can find them in this paper, which is now submitted. And in the arXiv, we see that first we go with the gamma, and then, so we're using this hybrid, and then we go with the inverse gamma. And we get this really, you know, pretty nice classification. In this case, what is noise? It's unclear because, you know, it's a data, classified data, so it will require a little more work to put the noise, you know, a generalization of the idea of noise in these applications here. So I don't want to go too much over time. Well, thank you very much, and I'm ready to take questions right now.
Thank you. Thank you very much, Daniela. There was already one question that was asked at the beginning of your talk, so I just invite the audience to write the questions while I read this one. So this question was asked by Ole Melnik, who was asking, I think it was about the time of the slide where you introduced the generalized gamma hyperpriors. So what's the benefit of this model? Since entries with small variance will not be zero, won't it be more convenient to use Bernoulli-Gauss prior, like Bernoulli random variables as selectors of non-zero entries and Gaussian as actual distribution of non-zero entries?
So I will say that there are many right answers. There are many possible choices here for this hypermodel. So the answer is yes. Why have we decided to concentrate on this generalized gamma family? Is because number one, computationally, it was very convenient. So we can apply, we have applied it to very large, problems. And we have these formulas for which we can do this, these updates of the variances in a very fast manner. But that doesn't exclude that other choices of the probabilistic model for the variances are also viable. This is, there is a lot of, as they say, right? There is a lot of space at the bottom. So yes, it's also worth investigating other models. The problem is, not the problem, the reason, the motivation for us to stick with this is because we had some partial results and they were not so easy to obtain. It requires, fixed point theorem type of approaches. We had we had to come up with an algorithm that was computationally efficient. Also, at some point, we were using it without guarantees, as we often do when things work. And then people kept saying, "Are you guaranteed that? Are you sure that it converges to a unique solution?" So we proved that there was a unique solution and that the algorithm was converging to that unique solution. And there was the question of when we're also generalizing, where we're looking at different members of the generalized gamma family which are more greedy. We really wanted to have some sense of can we rein this in, because we did notice that we got stuck, like everybody who's using non-convex functionals and trying to minimize them, we do get stuck. You do get stuck sooner or later at a minima, one of the spurious minima, that is not really meaningful for your solution. So so it was more of, we kind of like, we wanted to complete our analysis for this family of, but yes, definitely, it's worth investigating using alternative hierarchical model. I think a hierarchical model is needed though, because, you need to model the variances.
Yeah. So I hope it's clear for Ole. I think I'm allowing to talk in case he or she wants to reply. There is another question from Subhadeep Mukherjee. Sorry if I can't pronounce it correctly. How are the parameters gamma j in the hyperprior selected, and how sensitive is the solution to this choice?
Okay, the solution. So that's the other reason. That's the other reason for sticking with a family that we got to be a little more acquainted with, because we can choose the eta parameter. So the eta parameter, and I went at the speed of a slow light through that slide, but the eta parameter was the one that if we are using the gamma and we're sending it to 0, essentially we're getting the same type of effect as if we were using weighted L1 penalty. So we can choose one of the parameters, which is the eta parameter, according to how sparse we believe that the solution is. Sometimes we think it's a sparsity as a belief. Like we believe a solution is sparse, but we don't know the solution because, as I usually tell my students when I teach, if we knew it, we wouldn't have to compute it. So, but we have a sense that it should be sparse, but sometimes we think, yes, it should be sparse, but it could be kind of sparse, but not super sparse. So if we have the doubt that, maybe imposing or more strongly promoting sparsity would push towards, favoring solutions that, say, may put too much trust in the sparsity, then we would choose an eta parameter that is a little less close to 0. Otherwise, if we want to push the sparsity mega times, then we choose the eta. So we use the eta like a screw for sparsity, and the tighter, the closer to 0, the more sparsity with gamma equals 1. With generalized gamma, well then, the parameters are a little more delicate. So that's one of the parameters. The other parameter, well, the R parameter is a choice of how much sparsity we want and whether we want convexity or not. So that's, you know. And then the other parameters are the var thetas. And the var thetas, so we have this, in the paper with Alex and Monica, we have this way of selecting the values of the var theta that correspond to, essentially they are proportional to the classical sensitivity weighing that have been used in geophysics for, like, I think since the 60s or 70s. So they've been used, and there has been always this discussion. I've had it with my colleagues from geophysics, like, how can Bayesians, you know, like, you're using sensitivity weighting, but, or we use sensitivity weighting, but we don't, you know, there is no justification. So right now we can justify it in a fully Bayesian framework. So
yes. Yeah, so there is one question from Hong Peng Sung, which is actually one question I wanted to ask too. So he's thanking you from your wonderful talk, and is wondering about convergence guarantees for the IAS algorithm that I mentioned. Yeah.
So yes, so we have a convergence guarantee to the minimizer of that functional if we are solving the least squares problem exactly. So it's a mathematical proof of convergence.
Okay.
And sort of it has to do with relating, you know, so there are several steps that go into it. That's why it's not appropriate for a talk, but all of the details, yes.
And whenever you solve it approximately?
When we solve it approximately, it's a little more difficult, right? Because to some extent, you know, we are relating the theta and the axis. So there is one is a solution of a least squares problem. We believe that if we solve it approximately, we get in a region where things are fine anyway, because after all, we also are also accounting for, you know, data with noise. So and paradoxically, so there is no, we don't have a proof yet. We don't have a mathematical proof of convergence yet when we solve it approximately, but we have evidence that when we're solving it approximately, we do better than where we solve it exactly. And also from the point of view of matching the data. And that seems to be because we're always using these Krylov subspace methods, and the right-hand side conveys, you know, it brings in a lot of information in the initial. So we're starting in some ways already advantaged, knowing, you know, we're building only the subspace that we need to know in order to come up with a solution. And the performance has been, let's say, even better than for the problems where we can do it when we're using a backslash.
Interesting, yeah.
I think it would be worth analyzing this a little more deeply. We've done some sort of, we've done some analysis, I think in the paper in 2015, where we've looked at what is approximating, what these Krylov subspace methods are approximating. And it seems like this idea of using the D, the matrix, right, D as a right preconditioner, it's kind of like spreading out the singular value more widely. So there is an approximation of those first of those eigenvalues that are more relevant for the right-hand side. So there is some weighing, but and we have actually, you know, I think at Alex showed a movie where he was showing actually how the Ritz values they were coming in, and yes, there is some information there, but we've not been able to fully explain that.
Yeah. Thank you very much, and thank you everyone. I may have a few more questions, but I maybe write you an email afterwards. So thank you again, Daniela, for your wonderful talk, and thank you everyone for attending. Just as a reminder, we are running these seminars every week, so I hope to see you everyone next week. Thanks a lot, and have a good day.
Thank you. Bye.
Thank you.